Good evening, everybody. I am very happy to introduce Professor Chen Change Loy to the audience. Professor Chen Change Loy is a President's Chair Professor with the College of Computing and Data Science at the Nanyang Technological University, or NTU, in Singapore. He received his PhD in 2010 in Computer Science from the Queen Mary University of London. Prior to joining NTU, he served as a research assistant professor at the Multimedia Lab of the Chinese University of Hong Kong from 2013 to 2018. Dr. Loy's research interests include computer vision and deep learning with a focus on image restoration and enhancement, generative tasks, and representation learning. He and his research group pioneered the research in face detection, face alignment, and image super resolution using deep learning. In particular, his paper on image super resolution was selected as the most popular article by the IEEE Transactions on Pattern Analysis and Machine Intelligence in 2016. Dr. Loy has a very large number of awards. He is recognized as one of the 100 most influential scholars in computer vision from 2020 to 2025 by A Minor. His accolades include the CCF-CV Test of Time Award, the Nanyang Research Award, and the Singapore Open Research Award. Moreover, he has to his credit more than 110,000 citations on Google Scholar. He has served as the associate editor of several prestigious journals in computer vision, the Computer Vision and Image Understanding Journal, CVIU, the International Journal of Computer Vision, IJCV, and the IEEE Transactions on Pattern Analysis and Machine Intelligence. TPAMI, or the IEEE Transactions on Pattern Analysis and Machine Intelligence, is one of the topmost journals across the length and breadth of computer science. Over and above this, he has also served as area chair for several prestigious conferences in computer vision, AI, and machine learning. With this, I'll hand it over to Dr. Loy to give us his talk from segment anything efficiently to matting anyone precisely.
Thank you. Yeah, thanks, Ajit, for the kind introduction. Yeah, go on. Yeah. Okay, good evening, everyone. Thanks for attending my talk today. So that's the title, but before I jump into my talk, just want to introduce our lab. So this is our lab space, and we have around 50 students and staff in our lab. And what I'm doing in my research is computer vision. I'm mostly using deep learning techniques. So computer vision, I mean, I'm not sure, maybe not all of you working in this area. In computer vision, what we want to do is that we want to enable machines to interpret and understand visual information like humans. Yeah. And the goal is to extract, analyze, and understand meaningful visual information from images, from videos, and to enable decision making. So typical questions that we ask is that what objects are in the image, where are they located, detection and segmentation. So later I will talk about the segmentation task and what's happening, like action recognition, scenes understanding, as well as how does the scenes evolve, like tracking 3D reconstruction. So these are the topics that we are doing in our lab, mostly in generative AI. For example, visual synthesis, we generate images, we generate videos. Visual editing, like we do image video editing, visual enhancement, graphics, and also high-level visual processing, for example, detection, segmentation, tracking, as well as a large language model or large multimodal models. So just to show a few examples, we have been doing super resolution for quite a while. And the task is to enhance low-quality image to high-quality ones with added high-frequency details. So it works with like natural images, building images, as well as we can use it to restore old videos, old footage. Yeah. And also, if you have like old anime or cartoons, we can use our algorithm to make it better looking. So we also do other image enhancement tasks, for example, image colorization. Yeah, this is the old library of Nanyang University. We can enhance, give the colors by just providing a text prompt. Yeah, this is old street in Singapore. Yeah, we can also give the colors to this old black and white photo. We do a lot on visual editing. For example, in this case, this is the lady with the brown hair. We can change the hairs, change the colors of the hairs, without affected by occlusions or movement of the person. We can also make a person younger. Yeah, ladies would like that. Yeah, so we can make the person look younger or a bit elder. And this works on video as well. With our techniques, we have a lot of basically a stack of technologies that can be combined together. For example, post-estimation, segmentation, impeding, retargeting, harmonization, and we can achieve complicated tasks using these technologies. For example, we can do post-estimation, we perform segmentation, then we impede it and replace it with a robot. And we can generate videos by using diffusion model. And just need to provide the text prompt, and then we can use diffusion model to generate the videos. And this is another example. And we can also use a text prompt, fit it into our model and generate a 360-degree panorama scenes, where you can wear a goggle and then you can just immerse yourself inside this 3D world. So all these are synthetic, so generated by our method, and you can easily place object into the scenes and then with good with plausible rendering. We also do like 3D reconstruction. Based on just like single video, you can reconstruct the humans, 3D pose, and the shape, and we can render the shape using virtual avatar. So you can convert yourself in a molecular video to a virtual avatar like this. Our recent work also explore kind of dynamic 3D reconstruction. Basically, you can walk around with a camera and then collecting the images. And with these images, you can fit it into our algorithm to construct the 3D scenes. That would be very useful for like heritage preservation, or you can use it for like building reconstruction. Okay, so today I will just talk on two topics, basically on segmentation and mapping. So these two topics are related to each other. So it's done by my students. Basically, Zhou Chong, he has done these two pieces of work. Try to improve segmentation and fit it into mobile devices so that it can run in real time. And then Pei-Ching, is working on Matt Anyone, basically doing video matching, precisely for human portrait. And given the time, I might not have time to cover the last work. It's done by another student, Suzhe. Okay, just a little bit of background about semantic segmentation. Is a classic problem in computer vision where you feed an image into your model. You will get pixel-wise labels as the output. For example, like this. So you want each pixel to describe the object as the object of interest. So in conventional semantic segmentation, you need to pre-specify the object categories, for example, 20 categories or 50 categories. So it can only generalize to limited set of categories. It doesn't work on open set. And you also need to provide the object bounding box as a condition as well, so that you can pinpoint the object that you want to segment. And the bounding box has to be accurate. There's no so-called flexibility in terms of interaction. In most of the cases, if we do not provide a bounding box, if we provide a point, then the algorithm wouldn't work. So in 2023, Meta basically published a paper called Segment Anything model. We call it SAM. In this model, basically, is a foundation model where you can it allows interactive segmentation. You can just provide a point, or a text prompt, or a bounding box. Then you can segment the object of interest. It will be very useful for embodied AI, where the robots need to understand the scenes. So you can kind of pinpoint the exact segment of the object. And also important for this kind of scene understanding, where you want to understand all um, the area of the different causes of the scenes. Okay, so this is the model architecture of the SAM model. Basically, it comprises of the encoder that encode the image into some embedding, and there's a mask decoder that decode the embedding into the mask as the output. And there's a prompt encoder where it can take mask, points, and box, so that this is defined by users. For example, you point it to the flock, and then you can get the flock mask as the output. So it's it is a fully interactive. So to train,
also take a text prompt?
yeah, it also take a text prompt. Yeah, but I didn't put it here. So to train this model, you need really large scale data with 11 million of images and 1.1 billion of masks. That basically consume a lot of cost to annotate this data. So they do it in a semi-supervised manner, but it still consume a lot of human effort to get this data. And you need a really big model to to train and to take this data. So the model is huge. Yeah. So this image encoder alone, it has like 600 over millions of parameters, and comparatively, the mask decoder and prompt encoder, they are very small. So if we want to run it on like a GPU, that's fine, but you have a very low frame rate, 4.3 frames per second. You can't really run it on iPhone 14. It just report out of memory. So what we really want to do is that we want to migrate this model into mobile phone so that it can be useful for many subsequent tasks. So in order to do this, the general idea is to compress the model. One way of compressing the model is through knowledge distillation. This knowledge distillation is proposed by Geoffrey Hinton. And what we are doing here is that we have a big model that we want to compress, and it contains it encapsulates a lot of knowledge within this big model. We call it teacher. And you try to approximate this bigger and more complex neural network by a smaller and lightweight student with much lower number of parameters. So you want the student to learn the teacher's function, okay? And this can be done by transferring some knowledge from the teacher to the student. And one way to do that is through transferring the hidden activation. For example, if you have a sample, then you feed into both the teacher and student, you get the embeddings, and you try to match the embeddings. Optionally, if the embeddings have different length, then you have a regressor to convert this embedding to the same length of the embedding of the student. Then you do the matching here by minimizing this objective, and the knowledge can be transferred to the students. Basically, through the matching, the loss, you get the gradients, and the gradients is used to update the students. So through this way, you transfer the teacher's knowledge. We call it dark knowledge from the teachers to the student. So back to the segmentation anything model. We can also apply knowledge distillation to distill the knowledge of the original SAM model to the much smaller model. And that will, the destination basically focus on the image encoder, which has 600 millions of parameters. So this work is kind of previous work done by other research group. Basically, they did distillation using feature distillation. Yeah, they distill the knowledge from the teacher to the student, and later they discard the teacher and use this student for the deployment. So, and they basically in our research we found that in this kind of distillation is not optimal because distillation doesn't consider the prompts. Basically, it doesn't consider the user interaction. Yeah, it just considers the embedding itself, and it doesn't consider the decoder as well. So we need to consider both the user interaction and the decoder. And the backbone selected, which is vision transformer, is not friendly for mobile devices. So we need to choose another encoder, yeah, for this part. So this is another work by Meta. Basically, it's called Efficient SAM. It's published last year in CVPR. So they came out with a more sophisticated way to perform knowledge distillation using MAE or mass autoencoder, but they need like a full complete set of data, yeah, 11 millions of images to train the model and to distill the knowledge, which is not scalable. Yeah, we don't really want to use the full complete data set. Can we use a smaller subset to train the student? So we answered this question in our paper. It's already accepted in a journal called IJCV. So the main contribution is so-called prompt-in-the-loop distillation, where we make strategic use of the prompts to enhance the distillation. In other words, we consider user interactions, yeah, during the distillation process. And with that, we can improve the data efficiency. Yeah, in that we only need to use like 1% of the original data set to train the student instead of 100% of the data. So instead of 11 million images, we just use 1% of that data. And apart from the data efficiency, our model, yeah, with special design, with the distillation, we can run it in real time on iPhone 14. Yeah, it can run over 30 frames per second on common iPhone without any network quantization. So it's over like 37 times faster than the original SAM on the NVIDIA GPU card, and 7 times faster than other competitors on iPhone 14. So just a brief kind of introduction of our method. Our method is called prompt-in-the-loop distillation. It's divided into 2 stages. The first stage of distillation basically follow the notion of knowledge distillation. We want to extract the knowledge, encapsulate it in the original SAM encoder, and transfer it to the student, which is our HSAM encoder. And this is done using a distillation loss. This is nothing special, but what we really want to highlight here is that it's very important to choose the right backbone for the encoder. As I said earlier, for mobile devices, it's more kind of it is optimized for CNN or convolutional neural networks, and not for vision transformers. So instead of choosing like vision transformers or a hybrid version of them, we try to use a CNN version, yeah, that basically takes kind of inspiration from VIT design to get a better version of CNN that was published by another research group in CVPR 2024. And we use the model as our encoder, and we can achieve much faster basically runtime, yeah, for the SAM method. And if we, if with our method of distillation, our method actually perform very well, very stable. Yeah, if you give a budding box, yeah, it kind of give you a good segmentation. Yeah, with a point and it contains some noises, but overall it gives you very good segmentation outline as well. So that's the first stage of distillation. The second stage of distillation basically consider the user prompt, yeah, in the loop. Basically, the decoder itself, yeah, it needs to take the user input, either the box or the point, yeah, or the text, to generate the segmentation. So occasionally, the output is not correct. For example, the teacher would get the tail, but the student missed part of the cat. Yeah, for example, this is the tail of the cat, but it kind of missed it. So this kind of a wrong segmentation that would be considered and also transferred back to the students. Okay, telling the student, okay, this time you need to make this correct, and you shouldn't make the mistake again. So this is like hard sample mining. So for those hard samples, we will reiterate and tell the student to do it right in the next time. So with this kind of prompt in the loop strategy, we can reduce false negative and also false positive. And the good thing is that it doesn't, it's not tied to any backbone. Yeah, we can use the same strategy for if we choose other architectures for the encoders. So we do some comparative analysis. If we use encoder only KD, which means we don't do the second stage distillation. This is the performance. But if we consider the prompt, yeah, mining hard negative in the loop, we can improve the performance. This is the mean IOU. Yeah, we can improve the performance a lot. And this basically +1, +2 points is when when the user interact with the model by adding more points to correct the segmentation. If you add more points, yeah, basically we can improve the performance further. And the gap, kind of the improvement margin is improved, yeah, compared to using the first stage distillation. We can improve it by using in the loop strategy. So
here prompt is not some text. Here we are just naming that this is not cat, this is like that only.
yeah, the point is focused on the wrong areas. Yeah. So I just want to show you some examples. This method basically work on images. Without our method, basically you are going to miss some hard regions like this, where there's a lot of background clutter. And with our method, you can improve the robustness of the method. So yeah, you can see the part of this part is very similar to the soil. The colors are very similar. So with our method, you can correct that. And we actually, yeah, we didn't stop there. We actually transfer the whole algorithm into mobile phone. We asked my student to create an iOS app out of the algorithm. So yeah, we did further engineering effort to make this happen. This is an app that you can download on iOS Apple Store, where you can kind of create the object and then remove the object and perform in painting. Yeah. It works pretty well for like small objects and also translucent object as well. Yep. So that's our method that works on image. Yeah, we improve the speed of the original SAM by 37 times, and we can run it on iPhone in real time. The next thing we want to do is that we want to use it on video segmentation, not just on image, but on videos. So on videos, that will be harder because we need to consider the temporal dimension as well. Yeah, it takes frames in a stream. to basically the meta research group, they also did something on video. It started from seven anything model. They have this structure, and in order to consider the temporal dimension of the video, they basically apply the encoder for each of the frames, and also the mask decoder to decode each frame into mask. So what is different is that in this new architecture, they need to implement so-called a memory encoder. So you need to remember what the mask that you decode in the last frame. You store it in the memory encoder so that you can reuse it in the next frame. In other words, basically you propagate the mask that you decode in the previous times and propagate it to the next prediction. So that's for you have a memory encoder, you have a memory bank to store the previous result, and then there's a memory attention that basically allowed interaction between the embedding of the current frame and the memories from the memory bank to get the new mask. Okay, so they introduced a new data set with a lot of video annotation to train this large model. Again, this model is pretty slow, can only run at 1 frame per second on iPhone 15 Pro Max. This is due to the very large matrix multiplication that causes the slow speed. So yeah, basically memory attention, it tries to perform a dot product between the image embedding as well as the features that you store in the memory. So if your vector is really large, then yeah, you need a large multiplication to do that. So we want to solve this problem, and the obvious way to solve this is that to compress the memory. So once we get the result from previous frames, when we encode it, before we store into the memory bank, we ask the question whether we can compress this frame level memory mapped into like more compact tokens or more compact embedding, so that when we retrieve it from the memory bank for attention, it's much more scalable, much more feasible. So the main method that we apply is so-called perceiver. So the original perceiver basically is shown at the left-hand side over here, where you allowed a learnable query, and this is your memory, and you can compress the feature mapped to the same size as your learnable query through some cross-attention and self-attention mechanism. So basically, this query performs a global attention on the input features over here and outputs a single vector as a summarization. And this is the assisting perceiver. So what we try to improve is that we want to make it more spatial aware, in the sense that when we compress everything into a single vector like this, we lost many spatial information in the image. And we deal with segmentation, spatial information is very important. So we want to preserve those spatial information. So that's why we introduce a 2D a spatial perceiver, where we have a query like this. Instead of just one single vector, it's a matrix. And this query basically is enforced on local spatial region of the feature mapped. So that it can, each token here is used to summarize the information of each small patch in our image, in the full image space. Each token only care about one local region over here. So in that way, when we perform the summarization, the spatial information can be preserved, and we can maintain the spatial structure and reduce the total number of tokens. And we can integrate that into the SAM2 and speed up the memory attention by 8 times with comparable performance. So the
Like this spatial structure, what you are saying here, like in I work with satellite data, so that has we have geostatistics, variogram, semi-variogram kind of things for that spatial distribution of things happening in the surface. But this is the image; it can happen anything. So how you are presenting that spatial structure?
so how to represent which space?
Like that dark space.
That
So,
space. Yeah, that space is basically it comprises many channels from different level, kind of different hierarchical levels of features, and also the mass information itself. So it's high dimensional channels. Yeah.
so depth is there.
Yes. Yes. All right. So we have the spatial preserver. That's the architectural modification that we did to the SAM2 model. And we also perform distillation, yeah, to improve the kind of efficiency of the model. We follow what we have done in our previous work, HSAM, to kind of to use prompt in the loop distillation to transfer the knowledge from the teacher to the student. This is a much smaller model, yeah, the image encoder. And we also, since now SAM2 has the memory component, we also need to do distillation to allow memory alignment. So teacher has its own memory. Yeah, the memory bank has its own memory, and the student need to learn from this memory bank. So we perform knowledge distillation from the memory bank to this memory bank as well. So I skipped a lot of results, but just want to show you an overview of the results that we get. So basically, we can improve the speed of SAM2 from 1 frame per second to 16 frames per second on iPhone 15 Pro Max. You can use it on your mobile phone to do video segmentation. It's less obvious on GPU, yeah, but if you look at the iPhone side, yeah, the speed up is much more evident. Okay, that's the segmentation problem. How much time do I have? Okay, so I will make this really quick, yeah, given the time. So this matching is, we call it video matching. It's unlike segmentation where you just want to distinguish the foreground and background. So in matching, you want to distinguish the foreground, background, as well as those details as well, like the hair regions. So these hair regions, they are kind of very difficult to be separated from the background. Yeah, given the nature is tiny. Yeah, so in matching, we need to kind of estimate a coefficient called alpha, or it's called alpha map, that has values between 0 and 1 that define the kind of the weightage between the foreground and the background. So when you decompose the image, so it's not just binary decomposition, but decomposed by based on the alpha coefficient. For matching, you can use it for various applications. For example, you can introduce like virtual background when you do Zoom or virtual conferencing. You can replace the background in videos. For visual effects editing, yeah, we basically work in, we do alpha as well. So can we use segmentation for video matching? Like this video, that is very hard to distinguish the hairs from the background. And if you apply segmentation, yeah, on this kind of videos, you can hardly get the details that you want, yeah, from the background. And what we are trying to do here is that we try to apply kind of a specialized algorithm, yeah, to distinguish the foreground, like the hairs, better from the background. So video matching, unlike video segmentation, it has kind of additional challenges, especially these areas. Yeah, those hair regions are very difficult to be distinguished from the background. And at the same time, I mean, you need to have high quality detail extraction, and you also need to have accurate semantic detection as well. So there are like two problems that you need to solve in one single model. Um, in compare compared to segmentation, where you have a lot of data to train your model, in matching you only have very limited data to train your model. Yeah, in the age of like deep learning, you basically couldn't survive without like large data to train your model. But getting data for matching is close to impossible because it's extremely hard to annotate. And if image is still possible, yeah, basically it's impossible to annotate video, alpha-mate for videos. So just to make quick, yeah, we try to design a better way, a pipeline to collect videos from kind of collect data from different sources. We basically download a lot of green screens kind of footage, clips from different sources on the internet, and we use After Effects in Adobe to carefully tune the parameters to get the alpha regions and the foreground that we want, and we ensure that all the clips and ground truth are carefully selected to maintain the high quality in terms of resolution, without issues like, for example, without issues on like reflective objects, and without issues on like inhomogeneous core regions. Okay, given the time, I just give a.
So if you go back to the slide, when you take a picture of you right now, so you're wearing glasses. What happens is that the frame of your glasses will actually pick up the background because global illumination. So your mapping did not have data correspond. Am I making sense? Your spectacle is a good example. Right? If you're wearing some, if ladies wear some little thing on the top, then it actually captures that. So does the mapping do you address this kind of effects?
Yeah, we do address this. Yeah, this is a very common problem in matting.
It's in the interior of the face. It's not in the back.
Yeah, interior of the face. Yeah.
So you compensate for global illumination.
Yeah, it's mostly data driven. So we need to like collect a lot of data with such cases, and then train a model to recognize that kind of patterns. Yeah. So it's still not perfect. Yeah, the data is still not enough. Yeah, we are collecting more data using, yeah. Okay. So just a quick kind of introduction of a method. Since we are dealing with video, so as in the SAM2 like video segmentation, we need to have a propagation method that propagate the result of previous frames to the existing frame prediction process. So we have a specialized path and a module to do that. And but this has to be done carefully because when a person is moving, then there's a region that change a lot, and there are some regions that change a little. And for example, the main face region tends to maintain the same appearance as the previous frame. So in that case, we do not want to make overly different prediction compared to the last frame. So we try to maintain the kind of the last frame memory and output it as our previous prediction. But for those regions that move a lot compared to last frames, yeah, we have a memory bank that stores a lot of historical values from the previous frames, and we use a sophisticated method that perform attention between the memory and the current frame, and select the right memory to be as output. Yeah, there will be some adaptive fusion over here to combine the two different memories, the last frame memories and the memory from like much earlier frames. Yeah, just want to show you the final result. There are some details here. So this is the input video. Yeah, this is the method that we get. This is a very hard video that we are dealing with a lot of like soldiers at the background wearing the same uniforms. Yeah, we are not performing 100% perfect, but compared to other baselines, we are performing much better. And now you can do it for like human. You can do it for the object as well, not just human. Okay, it does very well on like fast-moving video, with actions. We can do like multi-instance video matching. Yeah, despite of occlusion. Sorry, say again.
For the multi-instance, do you do one pass or multiple passes?
Just one pass.
One pass.
Just one pass.
One pass captures all the questions.
Yes, yeah.
But you train it for multiple instances.
We train it for multiple instances. Yeah. So what happened here is that at the beginning, the user just need to select a point on the instance that it wants to perform matching. Yeah, it can introduce multiple points to the original video, the first frame of the video, then it can automatically get you the mask of each instance. Yeah, you can see the details that we can extract for the alpha map. Okay, we have a demo online where you can come upload your own video. Yeah, basically you just need to click one of the points in the object of interest, then it will extract the subject automatically. In this case, you can specify the object that you want to perform mapping and ignore other regions. So for example, this lady will be treated as background because I just want to get the foreground of the guy. All right, so this is the final slide. Basically, there's still a lot of limitations of a method. For example, in this homogeneous scenes where you have like white curve with the white snow, yeah, our method suffer. Yeah, we can't really get that. That requires us to kind of collect more data, more videos, and carefully design the model architecture to deal with this problem. And in the future, we want to again do this mapping on mobile phone, and not just for human, but also for anything, for dogs, for your pets. All right, yeah, we basically release all the code and demo online. Okay, thank you. Yeah.
Questions from the audience?
So, how does the image quality, basically from what I'm seeing, the images are pretty pristine, you could say. They're shot from an iPhone. And from what I could see, how does images not being in the best possible version that they could be? Let's say if there is a lot of sunlight which blocks the features, and then how could I improve this model to deal with such disturbances in the image, such noise that like the camera generates?
Yeah, this is a kind of is true challenge, yeah, to the model. Yeah, if you have like light illumination changes and also kind of severe pose changes of the object, then it might be difficult for the model. But currently, the main technique to deal with this is to carefully collect more data of these kind of corner cases, and then you try to tune your models better. And that also requires you to design better memory mechanism that store more context of the past so that you can deal with different changes. Yeah.
Okay, go on. I just want to go back to your first slide. We talked about computer vision. And this seems, I just wanted to get a sense from you, distinguished researcher. When you talk about computer vision, there's been historically many textbooks and many principles of textbooks which require mathematics. This doesn't require any mathematics. Am I correct? And so, how would you comment on how the field is?
Um, Interesting. Yeah, we still have mathematics, just that we do not show it. But but yeah, but I mean in like deep learning era, I mean people are like building foundation model, and this foundation model are data driven. They are so powerful. So in many downstream tasks, you you basically just need to fine tune it with some like target task data, then you can perform very well. Yeah, I don't believe that. I mean, with current methods, you can scale very well. Yeah, the scaling law is hitting the wall, as we know. So we really need something like back to mathematics, the theory, yeah, to kind of develop or invent some new architectures or new theories to make things scalable and more robust or less data hungry. Yeah, but I mean now most modern algorithms or solutions that are based on big data and big model, but I don't think that's the future. Yeah.
Thank you.
Thank you.
I have a quick question about your stuff. You showed something about flicker removal, which used a super resolution algorithm as the foundation.
Yeah. Uh, we do not do a flickering removal purposely, but when we train the model with the data that we prepare, we basically we augment the training data with a lot of flickering. We produce the data with noises, so it kind of help the model to capture this kind of artifacts and resolve that.
For the matte animal model, if I give it a video where in the initial few frames there is a foreground object which is very distinctly present, but in the rest of the video it sort of disappears or is only present at the very last few frames. Is the temporal module able to handle that very well?
Yes, if the object doesn't disappear for too long. Yeah.
Where I'm coming from, suppose so all the videos that you showed, there were people or in very good illumination conditions, building on what he said. So suppose if I this might sound nonsensical, but suppose I don't choose a person, I don't choose a very clear object or a person to be my subject, to be my foreground. If I choose, let's say, a bright but a very small flower in the background on a tree, and but I can make sure I gave it a video where it is distinctly present towards the final few frames, but majority of the frames it is not present. Something like a re-identification problem. Is Matt anyone able to handle that?
Yeah. Met anyone couldn't handle like overly small object. Yeah, I would say. I mean, if your object kind of have very blurred appearance, very bad appearance in some of the frames, then the arrows might be compounded in the memory. Then the prediction will be drifted away. Then it will be no longer able to track the object. Yeah. So I mean, these problems also happened in the model.
And so again, can it be used for a personal re-identification
Uh,
I mean, of course, we won't get like it's still a binary segmentation sort of thing, but still, can it be used in that sense?
yes, the memory attention mechanism is kind of achieve this kind of correspondence between a previous object and the object that you've seen in the next few frames. But it's a short-term correspondence being established here, not a long-term. For person re-ID, we really care about like long-term association, and that can be solved within this framework.
You started the same thing. So you said object categories, point, polygon. These are object categories. Uh, so all these can be seen from a larger abstract view also, like category theory, where we deal with different types of like some matrix can be there, some different structure which are preserving some self-preserving structure, like or we can only those things like geometry, this kind of what it makes sense for our, like my idea is coming from these are happening on RGB scale. So, but there are sensors which are capturing more data, which are not sensible for our like boundary. Like RGB we can make boundary whatever we see, but the heat signature that has different boundary. So that incomprehensible part from our human loop, is it there any possibility?
I guess he's trying to ask whether you're also using depth information in some of these tasks, like extraction of depth.
Possible, but we don't. Yeah, you can actually introduce more modalities like the depth information or other information that you feel useful to the model. Yeah, but we basically work on the RGB space at the moment. Yeah, you could consider that. Yeah, it's very flexible.
Okay, any more?
So I am showing the segmentation or mapping for you. You showed most of the objects have low risk. Will it work for which object is spread throughout the field? Like let's say it's some kind of operation. You consider
So if the object is not kind of in a homogeneous object, is spreading all over the space.
Like a cage pattern.
Like a cage. You can do that, but it might not be treated as a single object, but it's treated like multiple objects. We do segmentation for different. Yeah. You have to put multiple points on them.
That's still continuous.
Yes. Yeah, they can still track the objects, all the instances in subsequent frames. Just that in the model, it's not treated as a single object.
Okay, so let's thank the speaker once again.
Okay, thank you.
This is the motto of our institute.
All
It
right.
says Jnanam Paramam Dheyam, which means knowledge is the supreme goal.
Wow, nice. Wow. Thank you. Thank you for the meaningful.
Thank you.
Thank you.